This is my second attempt at standard 1.1, and it asks us to consider the quantum states, which are shown right here, and for each of them, calculate the probabilities of spin component measurements along the x, y, and z axis. So first, before we do that, we have to check to make sure that all the quantum states are normalized. So the normalization condition comes from the fact that the integral of the probability density for a particle that is at some position x over the integral negative infinity to infinity has to be equal to 1. This is basically saying that if a particle is measured, then there's a 100% chance that it has to be somewhere. Let's start with our first quantum state, which is shown right here. To normalize a quantum state, we usher in an overall complex multiplicative factor that we'll call C, and we solve for the factor by imposing the normalization condition below, which is right here. So we're just changing our quantum state. This is a ket right now, and we take the complex conjugate of this to get a bra, and we take the inner product of both of those and set equal to 1. Using this condition, we can normalize our quantum states. Here we have our complex multiplicative factor, and we want to solve for that, because that's what we want to multiply our original quantum state by, so it becomes normalized. So solving for C, we find that C is equal to 1, so the state is already normalized. And we can follow the same steps for this second and third quantum states, and we find that they are also properly normalized since their multiplicative factor ends up being 1, too. Now we know that our quantum states are all normalized. We can now move on to the next thing, which is to actually calculate the probabilities of the spin component measurements along the respective axis. The probability postulate in our textbook states that you can calculate the probability that a measurement on a input state will yield a particular result, a sub n, corresponding to the ket a sub n, using this formula. For spin component measurements, we are given the kets corresponding to spin up or spin down along the 3 Cartesian axes, and they are given in our textbook. Using these, we can calculate our probabilities. Let's start with the z-axis, since it is the easiest to calculate. For spin up measurement along the z-axis, this is how we set it up. So here is the ket corresponding to a spin up along the z-axis. Here is our first quantum state, and we're taking the modulus squared of it. Going through that, we find that is equal to 16 over 25 is our probability that we will measure spin up along the z-axis. Following the same steps for our second and third quantum states, find that they also have the probability of 16 over 25. For spin down, we do the same exact thing. We have our ket right here, and we find that that each of the probabilities for our 3 quantum states is 9 over 25, and this makes sense that since if we add the probabilities for spin up and spin down along each of the respective axes in each of the quantum states, they should equal 1. And 16 plus 9 equals 25, so 25 over 25 is equal to 1. So that's a good check to make while doing these problems. So again, it's following the same steps for a spin component along the x-axis. We find that they are all equal to 1/2. So then it follows that the spin down measurement along the x-axis for all 3 quantum states yields the probability 1/2. And for spin up, for spin up along the y-axis, we do the same thing. We take the, this is messed up right here, but this should be the inner product of spin up in the y direction with our wave function, our first quantum state, and the modulus squared of that. And we find that it's equal to 49 over 50. And for spin up for our second state function changes, so it's 1 over 50, and for our third it's also 1 over 50. So for our spin down, it follows that for our first quantum state it'll be 1 over 50. So we see that 49 plus 1 is 50, so that makes sense. And then for our second it's 49 over 50, and our third quantum state it's 49 over 50. Notice that all the spin up and spin down probabilities for each of the respective axes and quantum states add up to 1, since there's a 100% chance to make a spin up or spin down measure on each respective axis. Now part B, use results from A to comment on the importance of overall phase and the relative phases of the quantum state vector. From our results from part A, we can say, for example, let's take these two quantum states. One has where alpha and beta are two kets corresponding to quantum states, and A is a relative phase factor. These two quantum states do not correspond to the same physical quantum state and are not interchangeable. We see from the results of part A that when a relative phase factor difference between the two quantum states, part A, this was just a sign change, then we got a totally different probability measurements, and we saw that when we were measuring in the y direction or along the y-axis. However, for quantum states with an overall phase factor, they do end up corresponding to the same physical state. For example, if we look at these two quantum states where A is again an overall phase factor, these do correspond to the same physical state. In short, overall phase factors are considered unphysical and relative phase factors are considered physical.